Hello everybody. Today we're going to be talking about a topic in organic chemistry that is nucleophilic acyl substitution. Now if you don't know what nucleophilic acyl substitution is, I have a general schematic right here. It's when you have a carbonyl compound with a leaving group. This is known as an acyl group. And then you're going to have a nucleophile come and attack the carbonyl carbon to form this tetrahedral intermediate. And now, since you have a leaving group, you can reform the carbonyl and eject off the leaving group and then have the substituted acyl compound. So we're going to be talking specifically about the order of reactivity. And this is the order of reactivity you'll see. The acyl chlorides, or in general the acyl halides, are going to be the most reactive acyl compounds. Then you're going to go down to the anhydrides, the thioesters, and then the carboxylic acids and the esters are going to be about equivalent in reactivity. And then the amides are going to be more or less reactive. And then the most unreactive that we're going to look at is going to be the carboxylate. Now in each case, you see that we can identify the leaving group as marked in red. We're going to have a chloride ion over here. We're going to have a carboxylate ion as a leaving group in the case of the anhydride. We're going to have a anionic thiol essentially over here. Then we're going to have a hydroxide in the case of the carboxylic acid. Then we're going to have an alkoxide in the case of the ester. And then we're going to have a negatively charged nitrogen in the case of the amine. And then the carboxylate, if we did get a leaving group, we get this oxide anion. So the way that you typically know the order of reactivity is based on the pKa of the conjugate acid of the leaving group. So in this case, I'm going to actually explain to you what the pKa is before I get into that. So if you look over here on this part of the board, we have a general equation for acid dissociation constant, where our acids turns into our hydrogen ion and our conjugate base. And the pKa is defined as the negative log of Ka. And if you don't know what Ka is the equilibrium constant. That's then the concentration of the acid times the conjugate base over the concentration of the acid. And that leads us to our final equation for pKa right here. Is the negative log of the acid concentration times the conjugate base divided by the acid. Now this looks complicated, but what it's really telling us is as the value of the acid increases, if it's a more powerful acid, since this is a negative log scale, that means this pKa value is going to get lower. So low pKa value means high acidity, and a high pKa value means low acidity. And we know if something's a strong acid, it's going to have a weak conjugate base, and then the opposite is also true. If something is a weak acid, it's going to have a strong conjugate base. So now we can go back over to our acyl groups and see how that relates. So the conjugate acid of our chloride ion is obviously going to be HCl. And the pKa of that is roughly about -5. So let's go over to our carboxylate. We can see its conjugate acid is going to be a carboxylic acid. And its pKa value is going to be roughly 5. In the case of this species, we see that a thiol is going to be the conjugate acid. It's got a pKa of about 9. When we get to water, we should know the pKa value is, this is water as a conjugate acid, and the pKa value is about 16. Now over to the alkoxide, we see its conjugate acid is going to be just simply an alcohol, and then their pKa value is about 17. So now we can see the pKa of the water and the alcohol are about the same, and that explains this trend of the carboxylic acid being about the same reactivity as the ester. Now that we come over to the amine, we see that the conjugate acid is going to be amine, which you know is a strong base. So its pKa value is actually about 35. Now over here, we see for this oxide anion, the conjugate acid is actually going to be the hydroxide ion. So this pKa, I don't know if it's exactly tabulated, but we're just going to say it's very high because we should know that the hydroxide ion is not probably going to give up an extra hydrogen to become an oxide ion. So this is just not going to be very reactive. So in terms of the pKa, now we see what it's saying is when we have a low pKa value for the conjugate acid, that means the leaving group is a weak base. And we know basicity is correlated with nucleophilicity. So then that weak base is going to also be a weak nucleophile, and that makes it a good leaving group. So that's how all this table is explained. Now all of these pKa values are tabulated in pKa tables that you need to memorize or will be provided for in your classes. And I hope that helps everybody understand how pKa is related to the order of reactivity in nucleophilic acyl substitutions. Thank you.